Thank you, Renu. So I'm on the organizing committee, and this is one of the things that really got me interested about this conference. Being an observer is having some discussion about all these different techniques. You've seen a plethora of them this morning, and I know it can be pretty confusing about which ones to use when. Currently, almost all of them are limited by technology, and we want to get to them being limited by physics. And that's something I think all of you will be able to do because you're young, unlike me, and you'll be able to make a lot of progress in these techniques, some maybe more than others. So in discussing these techniques, and I brought this up with the organizers here and the rest of the SOC. And I thought it'd be great, since we're in Southern California, home of television, we could have a game show format. And we could, you could ask the tough questions, and then the person would have to defend their technique, and then some would lose and we buzzed out, or else we could do some wrestling, but this was quickly vetoed. So unfortunately, for better or for worse, we have a panel discussion now. So we will present some food for thought and then open it up to questions if that works for everybody. And yes, if I could also have the timer, that would be nice. Okay, so I had asked, I guess we have another microphone too. Is this okay to give to the panel? Okay, so I'll just have another mic here in the panel. So I had asked everybody, all the speakers from the morning, to give me just a few summary bullets to make things simple about the different techniques. So, and pointer is, do we have a functional pointer today? Thanks. All right, thank you. The top one. Okay. All right, great. So Jason gave us info on the direct imaging this morning. And then we heard from Hannah on transmission spectroscopy, Laura on emission spectroscopy. These are both for transiting systems. They're time resolved, not spatially resolved. And then we heard about high resolution spectroscopy from Matteo, who's also with us online, I understand. So don't diss high resolution spectroscopy. All right. And this is something that is velocity resolved. So another way to separate the star and the planet. And then from Sascha on nulling interferometry, which is also a spatially resolved technique. So Jason went to, so I'm not going to read everything on here. We learned that the spectra give us abundances, pressure temperature profiles, and astrometry for some of these techniques. High resolution's a little different. It's a little harder to get the abundances because we don't have continuum, but we also get information on winds, rotation, and then the nulling can also give us this spectral information, as we learned, also astrometry, the images that Sascha showed. So Jason talked about the current state of direct imaging and spectroscopy, which from the ground is, and also from space, is looking for systems that are moderate contrast. Right now, we're limited to about 10 to the -6. And that's actually sort of both the ground and space, depending on where the spatial separation that you're looking at. So this is limited to young stars, young systems, because the planets are bright, and things that are relatively bright compared to the stars. We heard from Sascha that if you want to look for Earths around mature stars, then you need contrast of like 10 to the -10. So future, there are plans to get there in direct imaging, but from space with this Habitable Worlds Observatory. Now, also, we saw these great spectra from transmission and emission spectroscopy, all these great web results. So why don't we build a bigger transit instrument next? And I'll argue is because we'll never beat the photon noise. I think these two techniques are pretty close to actually their physical limits now. We're getting within about 10% or 20% of the photon noise for Webb after, the experts massage the data, like Taylor and Laura and Kevin, are leading us through these exercises. So we'll need to advance from that. If you look in the decadal survey, I didn't read it all, but I did use the search function, and transits are just really not mentioned there. And that's why, because we are getting to the fundamental limits there. And for nulling, we saw that we're getting some results now on the ground, but as Sascha said, the background is high on the ground. We need to go to space to make it more useful for general studies. Let me see if I'll make a few more comments here before opening up to the panel and you for questions. Direct imaging. So yes, I was saying transits are limited by the photon noise, right? You always have the star there. So just to give you a picture of that, in case it's not obvious. Oops. Yeah, so this is this cartoon that Hannah provided. And you saw similar things also in what Laura showed and Hannah showed. So in transmission, the signal from the atmosphere is like that thin little blue annulus there. That's a really small area compared to the star. And you get so you need the star to light up that annulus, but the star is too big and you get all the noise from the star. And so that's what's really hampering us there is unless people can figure out how to shrink stars. And that's why there's all this interest in, one of the reasons why there's all this interest about M stars, right? Because the stars are smaller, so there's less noise there. So that's an ultimate limit for the transits. And then, yeah, Jason showed us the imaging on the ground now. Any other comments? So Roman is going to sort of approach the contrast needed for mature giant planets. That's going to be pretty interesting. First, really high contrast space observatory using different techniques that's used on the ground. So I don't know that much about it and don't want to get into it, but using like speckle nulling to like dig big holes as opposed to for contrast as opposed to fast AO. I guess there is speckle nulling done on the ground, right? Yeah, but it's usually has to be coupled, right, with the AO. Yeah. So, but the stability of space, where you can spend hours doing this to like beat down speckles, is going to be a big advantage. Okay, and then one thing too about the physics. So coronagraphs are going to be degenerate in the sensitivity and the angular resolution, right? Because the sensitivity is determined by how much light is collected by the aperture. And what do you know? As we heard, like diffraction is also determined by the size of the aperture, the size of the airy disk, right? So what if you want to observe something that is high contrast but really close? That's going to be hard to the chronograph. It's going to be hard to beat the airy disk of the star. But if you use something like a star shade, which we haven't heard about, that can actually break that degeneracy, because you've got the sensitivity from the telescope, and the star shade can give you the angular resolution that you want. So other things that I haven't said is that so the nuller can also break that degeneracy between because as we saw from Sascha, that you just change the distance of the two telescopes to get the resolution that matches what you need to detect the planets. So these are physics sorts of things. I will pretty much I try to shut up now and pass the mic on to other panelists that want to talk about correct the incorrect assertions I made about their techniques, or make comments about other techniques. And we have some more things we want to do to simulate discussion. So I'll open up to the panelists first.
Eclipses are the best.
Okay. Yeah. Oh yeah. No, eclipses are great. No, Laura and I think are proof of that. But if you can do them, yeah.
I just want to say that we are nowhere near done with transits or eclipses. Yeah. So even though the decadal might not have said that, it's not talking about the stage that we occupy right now. And there is a huge amount of phase space in terms of the planets that we can look at that we have not pushed the limits on yet. In fact, I think there is a huge amount of distance that we have to go with these kinds of worlds that we can push down in their mass, their distances from their star. We can go to cool cool Jupiters with these techniques. And I think that that's something that we need to really explore and use the telescope to its maximum. I don't actually agree that we have reached the noise floor. I don't think that we have fully pushed the limits of every single one of our instruments. And we can see that actually coming up with cycle 3 for JWST. There's new instrument modes being put on sky that we can use for these kinds of techniques, transiting time series observations. So we will see an evolution of this, that we've got 20 years with this telescope. We are seeing hundreds of planets being looked at in the first year alone. We have thousands to explore, and I reckon that we will, and that will offer us a huge insight into what these planets are like, which we can't do with the 50 direct imaging planets that we've got.
Oh, fully agreed. And yeah, it's great we have 20 years, because it's going to take us more than 20 years to build the next observatory. And I agree about that. Also, if you wanted to build, okay, thought exercise, if you wanted to build a bigger transit telescope, the thing, when you're limited by photon noise, signal to noise goes as aperture, the linear aperture, not by area. So if you want something that's like 4 times the signal to noise, you're looking at 25 meters in space. So that's going to be hard. So that's another reason why, yeah, I didn't mean to cast shade on the science of transits and eclipses. It's going to be our bread and butter, I think, for spectral characterization.
Yeah, and if I could just quickly add to that, I think that history has shown us from Spitzer and from Hubble that it's taken many years to get the most out of these observatories. And JWST is a little bit easier, like the quality of the data is higher, but that just means that we can push the telescope even farther. So I think it's going to be a very busy time for the next 10 years and beyond.
I'll just say for direct imaging, we always talk about this like Earth 2.0, Earth's mass planet at 1 AU, reflected light. But as we've seen in exoplanet science, there's this whole diversity of worlds out there. And I mean, we use that kind of as an advertising yardstick of what we want to get to, but there's a lot of stuff to do in between. And that's where the complementarity of all the techniques will be really interesting in the next 10 to 20 years.
I also wanted to say on the high-res side of things that I don't think we are scratching really the bottom of, we are definitely not at the photon limit. By definition, the technique is systematic dominated still. And all we do so far is to be on the safe side, is to throw away sometimes big chunks of data that could be useful and used. So there's definitely, I would say, like the limit of the technique at the moment is mostly on the analysis side of things, and mostly in the way we treat the removal of telluric lines. So there's potentially still quite a lot of road to go before hitting the very limit. But if we are talking about bridging 4, 5, 6 orders of magnitude, obviously this is not a technique to go. But as Hannah was hinted to, if we are talking about exploring a wider region of the parameter space right now, we are still far to have completed that journey, I'll say, with high res from the ground. And just like before getting back to you, like the point on absolute abundances, for instance, was a bit of a contentious point up to the 2021 paper by Mike Line, where we really rediscovered what stellar astrophysicists knew, that it's actually the line shape, the relative ratio between the molecular lines that dictates a lot of information about the abundances. And that information is still there, is still preserved. So even without the continuum, if the data is good quality, we don't actually miss the spectral information to determine abundances to very high precision. Obviously, there's a level of uncertainty of whether you trust a group's data analysis or the reliability of the instrument as a whole in terms of systematics. That's a whole different route. It is definitely harder to accept or treat than a space telescope like JWST. On that I would agree.
Yeah, I totally agree. Absolute abundance is not equal continuum. Like continuum does not equal absolute abundances. That's a misconception.
Maybe, we should open it up to the audience, and maybe first open up to. So Mike Line had his hand up, and we're like talking about him. So maybe.
This is fun. Matteo addressed my qualm about that point, so I won't go into that. I will agree that the biggest weakness there is the slow rate of change of orbital velocity. I think that will ultimately be the limit to high res. But if you can keep pushing your spectrographs to higher and higher resolutions, right? An R of 300,000 is 1 kilometer per second, right? So you can keep pushing your resolution to separate that. So that could be an instrument limited thing. And as we get better with these telluric removal things. So now I have like a depressing, sad question comment here regarding transit spectroscopy. So a lot of and you guys can correct me, I feel like a lot of the field, at least from my perspective for the past 10, 15 years, has been pushing towards smaller, cooler, rockier, right? And so the only way to really do that with the transit spectroscopy is to go around these M dwarfs, right, because of the transit depth ratio. So let's say, after say cycle 3 or whatever, we learn that none of the M dwarf planets have atmospheres, a very real possibility, right? Because M dwarfs are spewy. Where would that leave transit spectroscopy? Let's say, would we have to look for planets around K dwarfs? Is that possible? Or do we all just give up and say, oh, well, we have to do direct imaging? Where do we go? Like, I can see this train wreck happening in like 5 minutes.
You want to go first? No, I can. So you get an answer from me, right? Is it okay, Mike? Okay. So first, even if, well, whether or not they have atmospheres, let's see. Okay, let's take the data. Let's invest time. It's not. Let's see. Let's wait. Then even if the answer would be, it looks like there's not strong indications for any thick atmosphere, it's still low numbers, right? There's still room to play. I think this is why the ELTs and also, other future space missions, we should not disregard the M-stars too quickly based on small sample statistics. So that would be my current answer to the question. Let's first do the measurements as good as we can. We had a short discussion over coffee, right? I think this is one of the best and uniquest experiments James Webb can do. Right. So I'm not on the TAC or anything, but, if people on the TAC are here, trying to get more time for the TRAPPIST system to really nail down these small, I think that would be just fantastic because it will have huge implications, as you were alluding to, for future ground and space-based experiments.
I don't think that we are as limited as you think. And I also will contest the statement that the transing observations will tell us that they have no atmospheres. What they can tell us is the limits on the types of atmospheres we can detect. It does not say these planets do not have an atmosphere. It says this is the limit to what that atmosphere's mean molecular weight, its extent could be given the information we understand, right? It's a little bit more nuanced than you put it. And I think that that's important, and that really defines some of the science questions we need to be asking as we're pushing down. And I think that some of the key information we're going to be getting is also coming from looking across that entire phase space from our giant planets, where we're getting these really amazing and beautiful spectral features where we can understand and explore the physics and the chemistry, because our models aren't right yet. How can we best test those models? We can use these giant planets, and as we push down to smaller Neptune and sub-Neptune size, to really, really examine what we understand about these atmospheres and the interaction of the different components. So it's going to take everything, and it's going to take all of us to really push those limits. And I don't think that we have a predefined limit right now. And I think there's tons of stuff that we're going to learn from that.
I also want to add, if they don't have atmospheres, that's okay. And that is if we can learn that, that is extraordinary. That is such an advance in human knowledge. And if they don't have atmospheres, that's still informative, right? That tells you about the initial volatile content of the planet, tells us about planet formation. And at least for some of them, you could learn about the composition of the rocky surface, which tells you about the geologic history of the planet. And so I don't think it's uninteresting. Of course, I'm on team atmosphere. I want to detect all of the molecules, but if we don't, it's okay.
Yeah, I'll second what Laura said. Also, Yeah, I see this as for like M stars too. So we're really sensitive only to like the latest ones. But Sascha mentioned the word ELTs. So I think that ELTs will be able to do chronographic techniques, because then in the near infrared, you don't need to get down to this 10-10 contrast between a rocky planet and an M star. So maybe we'll look at nearby like M5 stars with direct imaging and be able to get spectra of some of these things and be able to add up those spectra.
I like your answers. I'm just playing devil's advocate.
Now, this is where the game show format, I think, would have really shined.
So I'd like to bring up the topic, what's after these planned missions? Because let's say transmission, like everything that we can do on transits, we are not going to get new transiting planets. We are going to discover by the end of Plato and TESS, all transiting planets within 30 parsecs are going to be detected. By the time that we are doing the ELTs, almost every single star within 10 parsec will have a radial velocity survey that has detected most of the detection. Like we'll have a kind of an architecture sense of the planets within the 10 parsecs. So if the number of targets is going to stop, and we are going to do characterization of atmospheres within the 10, 20 years with James Webb and Ariel. Then afterwards, we are going to have missions like HubWorlds and Life. What's the next step? Like, where is exoplanet science going to end up? Once we get Earth 2.0, are we satisfied? Are we going to build something new? Are we going to build something to study doing microlensing follow-up? Like, is this interesting? Is there any science case that is interesting that will lead to a different mission that is not characterizing an Earth 2.0? Because that has been the drive. I mean, we are doing intermediate steps, we are doing endors, we are doing, but after that, do we have any motivation to continue? We are not going to detect more planets unless we go to the microlensing and have surveys or statistical completeness, but not detailed characterization is going to be over. So what else?
So I'm going to dream really big because we're talking 50 years from now. So I have two things. These are things that are already proposed in the literature. I'm just repeating them. One, we can build a 10-kilometer optical interferometer and resolve the surfaces of worlds. The other thing is you fly a mission far out to outer parts of our solar system, use the sun as a gravitational lens, use general relativity, and again, resolve the surface of worlds. So we can actually take images of other worlds look like and not just a point source. I think that would be really cool.
Can we take an online question?
Sure.
Right. So there's a question say, what is the best precision with which we can now measure relative chemical elements abundances in nearest exoplanets' atmospheres in best case scenarios? Do you want? So what's the best precision with which we can now measure relative chemical elements abundances in nearest exoplanets' atmospheres?
On the hot Jupiters from the ground is 0.1 dex. Give it or take it. So 10%.
Yeah, that's about the best I've seen in the retrievals my group is doing with web data. Has anybody seen any better? So now that also includes panchromatic data. So this is when you combine things like with web, we can go from 1 micron out to 12 microns or so, and like there are multiple methane bands, multiple SO2 bands. There are multiple bands of CO2, some stronger than others. So that's also gives us some leverage. It's not just the instantaneous signal to noise.
Yeah, no, it's exactly the same for us. Like there's no like individual line or like just one species. Like it has to be done all at once. Yeah.
I'll say for the direct imaging spectra, some of them are really good that the statistical precision is going down to the percent level, but we're really just limited by model systematic. So it's, you can't trust at some point you're limited by systematics rather than statistical precision. And we're starting to run into that, I think, in all of the cases.
Hi, everyone. Jorge Sanchez, ASU. We heard some really awesome talks today about the benefits characterization of exoplanet atmospheres at different spectral resolutions. And I wanted to ask the panel here about what are some of the benefits of combining the different spectral resolutions? What can be offered by this type of analysis? What can we get when we do this combination of low and high spectral resolution analysis? What do we get? How do they complement each other?
Matteo gave an example of that with like ultra hots. We're both getting the line emission from the high resolution and a lot of the molecular species from like lower resolution, including transits like James Webb. I don't know if there's any other comments on that. Yeah. Oh.
There was the case also of recent or WASP 18, right? Where when you start thermally dissociating water, and it becomes harder like to detect it at low res. High res can give you a little bit of a kick there to have the information about that species. So those are just isolated examples, but I'd say every case where the broadband information is useful to constrain some of the physics of your planet, but the narrow component can give you more information about the species that are present. I think that's the key game to play in combining high and low res. In general, I think with the excellent data quality of GWST, it becomes a bit of a question whether this should be done routinely or just on some individual particular objects, because obviously GWST will almost always have the edge, I would say. Currently, I know I should be more positive, but the matter of fact is like it's the generational leap that we had with some of the spectrograph a few years ago, but it sets the quality of these observations quite apart between high res and low res, and in some cases that can be head to head, but in most of the cases GWST I suspect would be much higher quality than ground. So the question is the combination still valuable in this case, because it's a lot of resources to invest every time you want to combine these data sets.
I'll ask a question of the panelists here. What about combining transmission and emission? Is that at all worthwhile?
Heck yeah.
Definitely do that. If you can get transmission and emission, if you can get full phase curves, do it. You get so much information. It's a really rich environment to get the dynamics of what is going on in your atmosphere. Combining the information on the chemistry and then the temperature structure is really key. And we'll see later on in the week when Emily's going to be talking about the 3D nature of planets, the different techniques that are being developed to look at these planets that in their spatial form. So throughout their atmosphere, seeing that structure through pressure and through the different angles that we can get on those planets. So there's a huge amount of information we have yet to see. And this time next year, we're going to have a completely different landscape of what we understand about planets.
Yeah, just to add to that, I think like we're learning how complicated exoplanet atmospheres really are. And like, it's not surprising in a certain sense, but we need all the data we can get, right? You know, like we don't know where the clouds are. We don't know what the temperature structure looks like in different regions of the atmosphere. And often the interpretation, the less data you have, the more degenerate the interpretation becomes. And so if you really want to understand what's happening, particularly in 3D, you often need transmission and emission. And high res, you know, high res probes higher in the atmosphere. It gives you the lion shape. We need all of it.
We have online. So this question is asked, how important will it be to know the stellar abundances as we move towards better characterizing the exoplanets? Can we completely characterize the exoplanet at some point without needing to study its host star?
A lot of our uncertainties come from our lack of knowledge of the star. We can measure the transit depth and the eclipse depth to a high precision than we know the radii of stars. So we're already limited by that knowledge. So having any knowledge on these stars, especially these abundances, is really, really key. And when we take some of the measurements we're making of these planets and we incorporate our knowledge of the stellar abundances, our uncertainties are actually become much larger, because you have to fold in the uncertainty on what that stellar abundance is. It is a tough measurement to make. So the more information we can get on that, the better. And the more elements we're looking at as well. You've seen already, we're really looking at the calcium and the iron. That's fairly easy to measure. But what is the magnesium, the silicon, the oxygen, the carbon for these stars? Because those are the really key elements that we'll be tracing in these planetary atmospheres. How can we relate that back to the stellar environment, which will tell us about formation and evolution of different planetary systems? So there's a huge amount of things in exoplanets, as always, that really need to come into play and work together.
Tara Featheroff from UC Riverside. Since we're speaking about the stars, actually, I wanted to ask about the difficulties encountered by each of these techniques for variable stars, and what do you need to improve further about the star to reduce that difficulty from variability, especially M stars, but not excluding other types of variability?
Yeah, you see, we're discussing amongst ourselves because this is a really difficult question. It depends on what kind of variability you mean, right? I think one of the trickiest issues is the fact that the stellar photosphere is not homogeneous, and so you can get spurious features in your planet transmission spectrum if you have molecules in the star's photosphere. What to do about that? You can do simultaneous monitoring, so you could measure the brightness of the star over weeks and try to characterize the spot coverage that way. That's not a perfect technique because the size and the temperature of the spot are degenerate, but it gives you some idea. I think in the end, we also need to just incorporate the star into the theoretical models of the planet. So we can't use a 1D static stellar model anymore.
So for the nulling stuff, you are interested in variability, because if your star is doing something like this, also the noise that you still see is doing something like this. So you have a temporal modulation in the signal. And this is exactly what you're looking for the planets, right? As the planet's rotating. So depending on how much of variability you have, over what frequency, you are in trouble or not. And that's why even at the percent level, we would like to understand this general global variability in flux. Near infrared would be fine. Optical, we probably don't care too much about, but near infrared, that would be very critical. And then in addition, you would simply like to know radii and effective temperature, luminosity as good as you can, because there was a question, how do you actually look at it, because you have the freedom in arranging your array or your baselines depending on what plans you're interested in. And when you search, we would like to understand the luminosity output of the star so that you can optimize the search for certain kinds of planets. Doesn't have to be the habitable zone, but certain separations. So, and this seems surprising, but for some of the stars within 10, 15, 20 parsec, all these things are not known to full extent. This is, we know all the stars basically, but a systematic and homogeneous analysis of fundamental stellar properties is not available. And this is something all the future, missions, ground or space-based, I think is absolutely crucial.
As a rule of thumb, I think that the emission spectroscopy of transiting systems is a little less subject to stellar variations than transmission. Also, particularly if you go to longer wavelengths or stars less variable, but also because you're not using the star light itself to probe the atmosphere when you're making that measurement. That said, emission observations are harder. It's just part of the general conspiracy of doing remote sensing science.
I'll just say for direct imaging, we're trying to spatially resolve things rather than using temporal. So the stellar activity doesn't matter, but for talking about things like habitable worlds, the finite angular diameters of stars start mattering.
For high res, even a known variable star in transmission is quite a challenge. because obviously there's a transiting planet across a rotating surface, so that's a strong signature to deal with. But in terms of variability, it's all about, it's a normalization factor. Like, it's true that we don't have the continuum, but we have the lines with respect to the continuum. So for some reason, the continuum of the star changes, we normalize our spectra to a different level. So that might result in systematic shifts in the abundances retrieved if we don't take that into account. This said, it hasn't been studied, so we don't have simulations yet that show that level of possible systematic error, and that's probably needed sooner rather than later. So.
And just right before the next question, it's about time for the poster pops to start lining up. So if you could do that, and now Paul Moliere will ask a question. Oh, there are two. Okay, there's another microphone. Okay.
Okay, thank you.
I think-
I just wanted to make a small point about something was said earlier, which is true. We only have like 24 or so directly imaged planets. But what we shouldn't forget is that we have an often overlooked target a bit in the field of expanse, which is brown dwarfs. And brown dwarfs actually are governed by almost the exact same physical principles, as we all know, more or less, than directly imaged planets. So we have an excellent training set for the actually test our models. We can compare the abundances that we retrieve for massive brown dwarfs, which are companions to stars, to the stellar abundances. So we can actually test things that we can never, I think, begin to test for real planets that we're interested in. So I think this is a really crucial planetary type as well.
Yoni Brandy, University of Kansas. Thanks for really great talks this morning. Something people have mentioned is the sort of wealth of data that we're going to have in the next couple of years and decades. But also, as Matteo brought up, there are some sort of theoretical and computational roadblocks, like likelihood functions for high resolution. What are sort of the major computational problems that you see coming up with this massive data quality increase that we're going to have?
With an increase in the wavelength coverage and number of data points, you have a increase in the number of free parameters in your model fits. The amount of things we need to now fit when we are looking at spectra is humongous. And if we start thinking about potential profiles throughout the atmosphere for different abundances and changing those profile structures, not just saying we've got this single abundance, you end up with multiple parameters per species you're looking for. So there's computationally, we're really expanding the parameter space that needs to be explored to interpret the measurements that we are making. And that is going to be a key area where we need to start understanding how can we efficiently do that, and how can we correctly account for that statistically as well? How can we present those statistics that and all the degeneracies that they map as well in a way that tells a story? So I think we need to be really, really careful with how we're doing that and push the limits, but be realistic.
Yeah, I had a comment on that too. So like with the web transmission and emission data, with the panchromatic stuff, I'm just watching the retrieval people. It takes a cluster and something like 5 days, right, to do a thorough retrieval at high spectral resolution. And then you combine the emission and the transmission, you do a global circulation models, and those take a similar amount of time just for one model, not to go through all of the parameter space. And there are people in the audience like Taylor, maybe others, are working on like machine learning techniques to apply to like grids of these GCMs to try to, beat that.
I just want to mention two things. One is, I think, a lot of the stuff being done in the ML AI world is really applicable in terms of especially things like gradient-based optimizations that will like really speed up computations in ways, and it's something we in the atmospheric field have not really leveraged. And I think the other thing we should think about when we're talking about using clusters and things like that is at some point we should start thinking about our carbon footprint in the supercomputing clusters, because these things take up a lot of power if you start running these for many thousands, millions of hours. Graphics cards the way to go.
Well, we're at the end of our time. I'd like to thank you all for some great questions and discussion, and thank the panelists for participating. And no bones were broken or anything. So what could be better?